Hi, my name is Jason. Today we're going to be going over vertical order traversal of a binary tree. For this solution, we'll be using depth first search. So, just starting off with the problem, the idea of this is we have this tree, and the ultimate result that we want from this is to pretty much return the traversal of this tree column-wise. And what you can imagine is basically this sort of scenario. We have 9, 3, 15, 20, and 7. So if you were to get this question in an interview, the first thing that you should always ask is the order in which these elements should be returned. So obviously we want to return it in the column-wise order, but the second part is that we also note we should also be returning it in the order that is, here we go, the value of the node. So first of all, we report the value of the nodes in order from top to bottom. So in this case, we have 3 and 15. And finally, we also report first the value that is smaller. So for example, if we have a tree like this, why don't I write it out just to be clear? All right, so we have a tree like this. And if we were to then traverse these nodes, let's split up column-wise. Because these two have the same exact positions, 5 and 6, we need to report the smaller value first, 5, since 5 is smaller than 6. And so we know the hierarchy now. We first sort by the column, then we sort by the row, then we sort by the actual value of the node. So now that we have this hierarchy, we can actually go ahead and start coming up with a solution. So I said earlier this is depth first search. Well, why is that? What we can do is we can start from the root node value, which is 1 here. Let's say we have a function defined, DFS, and we start at this root node 1. And what we can do is we can start off at 0, 0. And what that's going to allow us is, if we explore the left, what we can do is we can say DFS of 2, node 2, is simply row 1, negative 1, column. And finally, we can even explore, if we're doing a depth first search, let's say we're doing the left traversal first, we can explore this node, and we can explore node 4, and we have row 2, column, negative 1. And we can also do the same exact way the opposite way. So if we're going to explore this node right here, and let me do it in a different color just to be clear. Let's say we're exploring this node here, we would simply do DFS of 5, node 5, and increment row, and also increment the column, and on and on. So just to be clear, while we're exploring, here's our current algorithm. We can explore the DFS of a node. Simply, we also explore the row and the column. And what we can do is when we explore the next child node, we simply add 1 to the row, and if we're exploring the left child, if we're exploring the left child, then we can simply deduct 1 from the column. And if we're doing the same thing for node.right, increment r plus 1 and increment the column because we're exploring to the right. So another thing that we should do, of course, is we should define this as a function. And also, one additional step is in between, we should also store the values that we explore in a tuple. Well, why tuple? Because remember this sorting paradigm where we first sort by column, then row, and then by value? Well, one thing that's cool about Python is because of tuple values, let's say we store, so as you described before, column, row, and finally node.val. If we call res.sort, because we stored it in this specific order, it will actually sort it by column, row, and value, which we described before. So why don't we just go over our algorithm real quick. Node 3, and I'm just going to go ahead and write just the row and column values. So we have 0, 0, and if we explore 9, we go here and we explore 9, and we have the row and column value of 1 and column value negative 1. And then there's no children, so also need to add a base case, obviously. Otherwise, we just be recursively going forever or run into a none exception. If we explore this way, we get 1, 1, which is 20. And then finally, we explore this way, which is 15. And this value here is very simply 2, 0. And finally, 7, which would be 2, 2. Now that we sort it, we also know that these values, so if we were to actually look at res, if we were to explore res, it'd look like this. If our res array would be 0, 0, 3, 1, negative 1, 9, 1, 1, 20, on and on and on. So now that we've come up with the pseudocode solution, why don't we go ahead and start actually programming it? So I'm just going to leave this on the screen. And let's go ahead and start writing this. All right, I'm going to make this a little bit bigger. So we have res equal to this list. Node, row, column. And then simply what we want to do is simply say the base case. If node is none, just return. If otherwise, append the tuple column row node.val. And then what we do is explore node.left, row +1, column -1, and simply do the same for exploring the right side. And finally, call this on the root node. Now, after we call this function, we know we can just do res.sort to sort by, as we described, column row value for all the tuples. Now, how do we actually construct the output? Well, what we can do is we can simply say call equals none, and we can go output is equal to a new array. And for val in res, because this is stored as a tuple and we know res is now sorted, what we can simply say is, here's the idea for call, creating the output array. We first start off with column is equal to none. And what we can do is we can simply just iterate through the array, say, okay, is 0 not equal to none? Well, yeah, it's not equal, so we can simply add a new array, append that value, and then iterate to the next element. So now, and then update current column with 0. And we encounter 1, and that's not equal, so we can append a new array inside the output array and append the value 9. And we iterate over here, we see 1 is the same thing, update current column, see 1 is the same thing as the last column, append that, on and on. And if it's not the same column as we traverse through, we just simply add a new array and fill in the elements here. So what would that look like? Append. So this is what I was talking about. Appending a new array if the current column is not equal to the current column that we're exploring. And just update with this current column we're exploring. And if we want to append to the last element in this array, well, we just call output -1, which gets this last array in the array output, append the value, and very simply at the end, just return the output. And if we run this code, looks like I spelled that wrong. Well, and just to summarize sort of runtime solution and space complexity, if we look here, we have this depth first search exploration, and we know that depth first search basically explores every single node just once. So we explore all of the nodes. So very simply, this would traverse the number of nodes. So this part, this depth first search, would simply take up O of n. This for loop, because we have to iterate through all the nodes once, would also be O of n. So O of n plus n, well, that's just simply O of n. As for space complexity, we store the result inside one array and we store the output in another array. And every single time we add to the result array, the size doesn't matter. It's constant. So simply put, we add n where n is the number of edges. And here we also add n to where n is the number of edges to the output array. So space complexity is n plus n or O of n. So long story short, runtime, space complexity of O of n, and this is a valid solution. Regardless, I hope this helps, and thanks for watching.